Right. Welcome everyone to this new SIPTA seminar. So today we have Michael Beer as our invited speaker. So I will hand over the floor to Matthias. So please, Matthias.
Hi, good afternoon, everybody. My name is Matthias Vaas. I'm professor of reliability engineering at TU Dortmund University. And today I have the pleasure and honor of introducing my good friend and mentor, Professor Michael Beer, who is a full professor head of the institute at the Leibniz University of Hanover and holds many board positions, many leading roles in societies. I think if I would start mentioning everything, the time would be over again. So Michael will talk to us today about efficient reliability analysis under imprecise probabilities. And I think Michael has way more interesting things to say than I do have right now. So I would like to hand over the floor over to him.
So thanks very much, Matthias, for the kind introduction, and thanks, Sebastian and the team, for inviting me. It's actually quite exciting to talk to this fantastic community. And the presentation is about a topic which is basically imprecise probabilities, which should be of interest, I think, to the whole community. And I would like to talk a little bit about reliability analysis with imprecise probabilities. So as you can see already in the introduction slide, there is a thank to a very long list of collaborators. Among them also Matthias, Marcus, Matteo, many names you know. And that is a kind of summary of what we did in our community, in our closer community, in particular in direct collaboration within my institute with the Humboldt fellows like Marcus and Matthias, in order to develop these, let's say, methods for reliability analysis with imprecise probabilities. So that is mainly based on Humboldt fellowships and postdoctoral fellowships and the work in the collaboration with the institute. So let's start with the general question. I mean, what do we want to do as engineers? We want to go for a numerical modeling of physical phenomena, the structure, but also its environment. So a big picture in order to come up with a prognosis regarding, of course, system behavior, risk, and reliability, but even more kind of social impact, economic impact, hazards, and these things. So we look at a very big picture. So we have to deal with very, very big problems. So dealing with big problems means we want to make conclusions that are relevant in many respects. So our analysis needs to be close to reality to deliver results which are reliable and give us, let's say, a very good basis to make decisions. At the same time, we need to be numerically efficient in order to come up with conclusions relatively quickly. So we cannot wait for maybe 2 or 3 months to get a numerical result. So of course, if you look at these two things, there's a kind of, let's say, counterbalance between them. If we are close to reality, we need precise models, very sophisticated stuff, and that is kind of slow. If we are numerically efficient, that means we are usually using approximations, which may then not be very close to reality. And the biggest challenge, I would say, in this context is to deal with uncertainties. So if we want to deal with uncertainties, we have different choices. So of course, many people think about just aleatory uncertainties when we hear uncertainties, which means we look at, let's say, statistical variation, variability with a physical background. So that is uncertainty that we can't influence. But it's even more tricky and more demanding to think about these epistemic uncertainties, which come from, let's say, a lack of perception, a lack of insight, a lack of data, lack of knowledge, lack of information. So to handle these uncertainties is, I would say, even more tricky. But the nice thing is that epistemic uncertainties are reducible as we improve the quality of the information that we have and as we improve the amount of information that we have. And that one we can take advantage of. However, in the end, we need to deal with both aleatory and epistemic uncertainties in one analysis. Now, talking about epistemic uncertainties, there are still different pathways to deal with this kind of uncertainty. One pathway is the probabilistic pathway. If we have some information that we can, let's say, quantify and describe in terms of probabilities, I'm talking about subjective probabilities here, which are usually leading a kind of Bayesian approach, which is very powerful, but we need some probabilistic understanding of this type of uncertainty. If we can do that, then we have a distribution of models, and we end up with a distribution in the context of reliability analysis, distribution of failure probabilities. But if we don't have any probabilistic information and just say, okay, we have a kind of range of plausible models or something like that, information which is just bounded, then we should go maybe the pathway of a set theoretical description, and then we end up with imprecise probabilities, basically dealing with a set of probabilistic models over some range of imprecision. And then we can also implement interval parameters directly in this kind of analysis. For example, structural parameters which are bounded based on physical inequalities and these things. So if we are dealing with a set of models, we end up with a set of results, for example, an interval of failure probabilities. So the question was basically many years back, which kind of method should we use? And we actually checked literature together with Vladek Renovich and Scott Fersen about what's available. And we found that actually there are, I would say, 15 to 20 different concepts of imprecise probabilities around, maybe even more. And we said, okay, actually, all of these concepts do in the end the same, bounding probabilities of events of interest. There are slight differences in the approaches and the access, but in the end, they all deal with a set of distribution functions and a set of probabilistic models. So, and then we calculate bounds on probabilities. And of course, when we are saying bounds of probabilities, or let's say bounding kind of models, we can never be sure that we bound these models in a, let's say, absolute way. So there's always kind of room to play with it. And that is basically using a set of models that this set comes as a, let's say, confidence interval. So always associated with a level of confidence. And that makes sense also in terms of quantification. If you ask experts to, let's say, quantify epistemic uncertainties, it is relatively intuitive to make an expert say something like, this value is between A and B, and my confidence is 90%. This quality of this information is much better compared to when you ask them to give you the first two moments for a random variable. So that way, we associate these kind of intervals that we are dealing with a confidence level. And then we say, okay, how can we deal with this in a, let's say, mathematical way now? And one very intuitive pathway is to deal with probability boxes. Just say, okay, we don't have a single distribution function, but we have a set of distribution function, which is bounded by kind of bounding distributions. And these bounds of the distributions don't need to be distribution functions by themselves as a part of the model, in particular if it's parametric. But it's just bounds for a box of probabilities, a box of CDFs, basically. But then we say, okay, since all these boxes are actually associated with confidence level, when we vary the confidence, that can be wider or tighter. And in order to play with the width of the set, with the extent of the set, we thought fuzzy probabilities are a good pathway for that, which is basically a fuzzy set of p-boxes with the variable size of the p-box. So that way, we can play with the size of the p-box and also explore sensitivities of the probabilistic result with respect to the extent of epistemic uncertainties in the input. The other nice feature is then the processing. All these models basically capture imprecision in a way that we say we deal with a set of distribution functions where behind is a set of random variables. If we pick one random variable associated with one distribution function, we can use the complete stochastic framework for the processing. So if we deal now with a set of random variables, we can deal with the stochastic framework for each and every random variable covered by the set. And in order to find the bounds on our result in terms of probability, we just need to apply some kind of optimization over this range of models to find the bounds on probability of the event of interest in the result. Okay, sounds pretty simple. Technically, from a numerical perspective, that is a little bit demanding. So let's first look at how we deal with intervals. So say an interval is just, let's say, a quantity which is telling us we know bounds, but we don't know anything what might happen in between. So we don't have any additional information except these bounds. So sometimes people come up with the idea, say, okay, why not use maximum entropy principle and say, okay, the interval can be assigned a uniform distribution. But the deal here is that we say, okay, maximum entropy principle comes from information theory. So if our problem is not related to information theory, we should be very careful to do that. Because talking about an interval, it could be that a uniform distribution is behind, but it could be that some other distribution is behind. And if we don't know, we should capture all these cases with our model. And the worst case is basically if we are talking about a single unknown value, which is somewhere in the interval, and we don't know which value this is. That means we have actually a Dirac function behind, which we don't know. So if this point where the real value is just where the peak of the Dirac function is, and this point would lead to failure of our structure, and we don't hit it, we basically come up with completely wrong results. And the other problem is, if we just assign a uniform for the input, that is just one out of an infinite set of possible distributions, we come out with one result as a distribution function which has no meaning, because our assumption is purely based on information theory, or basically artificial. So we should be very careful with this kind of modeling. Instead, we should really use interval approaches to deal with interval quantities. And then we say, okay, but now we want to play with the width of this interval, because we cannot make sure that we capture really everything in the interval. Of course, we can try, but then the interval is very wide, and the associated results might be completely useless if probabilities are between 0.01 and 0.999, then it doesn't make any sense, of course. But that would be an interval associated with a very, very high confidence. So in the end, we say we play with the width of this interval, and we want to have a tool which can process intervals of variable size just in one shot. And this is a fuzzy set, which is an instrument to deal with a variable size of intervals. And one point to mention here is, which is actually very important, that the membership function of these fuzzy sets has basically not really a meaning for us. We don't pay attention to the meaning. That kind of model is just an instrument to process intervals of variable size, and that's it. So we don't go into this kind of understanding of the meaning of the membership function of fuzzy sets in this context. Okay, so then how do we deal with this kind of models in a reliability analysis? If we do a stochastic analysis, we need to repeat the model call. We need to repeat the finite element or structural analysis many times to get a stochastic result in a, for example, Monte Carlo simulation. If we then say we have interval parameters in our stochastic model, and we want to find the bounds on the failure probability, we would need to repeat the stochastic analysis. So we have basically already a nested problem. And then if we also play with the interval size now and use a fuzzy set, that would mean we need to repeat the interval stochastic analysis. So we have a triple nested problem here. And as everybody can easily understand, the solution of that kind of thing in a brute force way is completely hopeless. So the idea is now actually very nice, but very demanding, very ambitious. We want to do just one single efficient stochastic analysis and then use all the information from this one analysis to solve the whole problem, avoiding this triple loop. Now, there are generally two possible pathways to solve this kind of problem. The first pathway is to use interval arithmetic, which means we implement interval valued parameters and variables into our numerical algorithm. That is a very, very intrusive approach, and it requires a reformulation of the algorithm. And the reformulation is needed because if we introduce interval valued variables in an algorithm, we end up very quickly with a dependability problem. So if you have a stepwise calculation and we don't trace the dependencies between intermediate results, which are intervals, then we blow up artificially the interval size within 4 or 5 steps to huge intervals. So that can only be avoided by a restructuring of the algorithm, which is avoiding this kind of interaction between the intermediate results. The problem is that this kind of restructuring, avoiding dependability problem, is limited to only, let's say, a small class of problems, like solution of linear systems of equations and these things. But if it can be done, then it is very efficient. But in many cases, it can't be done, in particular if you have numerical solutions like iterative methods with nonlinearities involved, like in structural dynamics, or in particular nonlinear structural dynamics, then this kind of thing is hopeless. But if it can be done, it's very nice. We approach the result from outside the interval, finding a tightest enclosure. The second pathway, which is a bit more appealing for structural engineers, in particular if we are talking about dynamics and nonlinear problems, is to use optimization approaches. That means we go for an explicit search for the results of the intervals in the of the outcome of the analysis, of the response or of the failure probability. So even here, we have different possible pathways. We can go for some kind of intrusive approach, reformulating the problem in its structure in order to be able to exploit the topology of the problem and or to utilize kind of linear algorithms, linear algebra, and linear programming approaches to solve the optimization problem. That is also can be very demanding, but it can be very helpful if the topology of the problem can be represented in a kind of standardized way. The second pathway is non-intrusive methods, which mean that we want to go for, let's say, direct optimization to find the bounds of the result. And that means we need to lower down the dimensionality of the problem, because optimization in the very high dimensions is usually a problem, in particular if you have a demanding algorithm behind. So we need to combine this with model order reduction, and then maybe also using a surrogate in order to have a very fast representation of the underlying problem. And then a sampling-based solution for the stochastic part, so that we have a completely non-intrusive approach. So if we can manage to come up with that kind of solution, then we can apply it to a very large variety of problems. But of course, numerically, it's usually slower than using interval arithmetic. However, to use the optimization approaches, let's say in a sophisticated way, is possibly the best pathway we can go. In particular, if we can also use dimension reduction in these things. So let's look at the first example where we use the kind of, I would say, semi-intrusive approach. So that is a development which comes from my time in Liverpool with Edo Patelli and Marco De Angelis. So let's say we have a multi-story building, and we look for component failure, reliability of the problem. For component failure, let's say just some columns, and we introduce 244 random variables, and each one has two parameters which are not precise, which come in the form of intervals with variable size. So we represent them by a fuzzy set, like the one shown here. So we have a total of 488 fuzzy parameters in this problem. So we can imagine that we do an optimization in the 488 dimensional space. It's kind of hopeless. So what we model here is basically from a civil engineering perspective that we say, okay, sample size could be 10 to 15, something like that. If we go for 90% confidence level interval estimation, we end up with confidence intervals like plus minus 7.5% tolerance. So we just applied this as an academic example, put this tolerance range at the support level of the fuzzy set, and then try to solve this problem. Here we use a special method from reliability analysis, which is line sampling, in order to exploit the topology of the problem. So what we do basically is we transform the whole problem into standard normal space, so that all the random variables involved will become standard normal random variables, and the nonlinearity from this transformation goes into nonlinearity of the limit state, which is shown here. So then, once we have transformed it into standard normal space, the only thing that can change is the shape of the limit state surface here. And the position and the shape of the limit state surface is influenced by the parameters of the problem, which are intervals. Knowing how this transformation works, we can assess in advance which parameter will move the limit state far away or towards the origin of the coordinate system when I move the parameter to the left or the right. So knowing that, we can identify that parameter combination which moves the limit state closest to the origin of the coordinate system. So that means we pre-eliminate this optimization problem based on looking at the geometrical problem. Once this is done, we know which of the parameter combinations leads to the largest and the smallest distance of the limit state from the origin, and that corresponds to the smallest and the largest failure probability. So in the end, we just need to do two reliability analyses, one for the lower and one for the upper bound of the failure probability for each of the intervals. So, or for each of the levels. So in total, the whole thing can be solved with only 1,400 shots of the structural analysis, and then we get a result. But the result also tells us something very interesting. So here we see the failure probability on the right-hand side, depending on the parameters, which are fuzzy sets on the left-hand side. So it looks like when we make the interval larger and larger, that the interval of the failure probability will also become larger in a kind of linear way. But the horizontal axis is logarithmic scale. So that scale is actually in a nonlinear way. So when we then see also the numbers, when we do this analysis in a standard way, just picking the midpoints of the intervals in the input, we end up with a failure probability of 10 to the minus 4, which is quite okay for component failure. But if we consider the plus minus 7.5% tolerance range, which doesn't sound very much, we may change the failure probability by 3 orders of magnitude to 1 out of 10, and that is disaster. So that means actually a relatively small tolerance range in the input of the probabilistic parameters can lead to a massive change in the failure probability in the result. So the whole thing is very, very sensitive. So which means that to take care of epistemic uncertainties for a reliability analysis really makes sense, and it may prevent us from making very, very big mistakes in the design. So, but still, we thought we might need to go even further with some numerical algorithms in order to, let's say, produce the results in even more efficient way. In particular, if it comes to time-dependent reliability analysis. And that is now a development which was driven by Professor Faas during his time when he was a Humboldt Fellow in our institute in Hanover. So that is a very nice development, really, let's say, avoiding the big optimization in the probabilistic context, but removing this optimization in a physical way, let's say, into the physical space to pre-eliminate all this optimization problem and then have just one shot for the reliability analysis. So again, the idea is to find the parameter vector which maximizes the failure probability in advance. Say that can be done by this fancy equation. And that can be done based on the so-called operator norm theory, where the operator is now A. And A is an operator which is basically a linear mapping which relates the input Z to the response of our structure Y. And here we have the parameters theta, which can be intervals, and they are part of this mapping, which is basically the physical model. So this physical model can be a structural analysis, for example, a finite element model. And then the idea is to find that theta, which maximizes the failure probability just by evaluating the physical model without doing a reliability analysis. And what Matthias found was that operator norm theory answers actually these questions with this inequality in terms of the norm, relating the norm of the input set to a norm of the response of the structure A times Z. And there is this factor C, which is basically telling us by how much the norm of the input will be stretched to give an upper bound for the norm of the result, of the response of the structure. And then we see, okay, when we pick a very, very large C, there's no problem, we satisfy this inequality, but the deal is to find the smallest possible C, which is then giving us an upper bound on the norm of the result. And so we can solve basically a kind of optimization problem to find the smallest C based on evaluating our mapping model A, which is, for example, a finite element model. So now we need to pick the norms in some, let's say, meaningful way. Since this time-dependent reliability analysis is, for example, usually used in the context of earthquake analysis, we say, okay, we use P1 as infinity norm to focus first on the largest response to retrieve the first excursion, because we are looking for that point in time when we have the first exceedance of a threshold, so which means structural collapse, or let's say that the structure fails according to some criterion, and the input would be a kind of L2 norm, which is related to the energy content of the load, which could be an earthquake excitation. So here we can also play with these norms in order to match the physical background of the problem and then solve this optimization. So let's look at a dynamical problem like this. Say you are using Calhoun-Löwe expansion to represent the input stochastic field, and then we translate this excitation, which is a load, to the response of the structure with the impulse response function. So we have a relationship with this equation between input Z and result Y, and the red box is then the operator, which is representing this kind of mapping. So then we can imagine that we can play with the input, we can calculate the different kinds of responses, and that depending on parameter vectors theta, theta1, theta2, and so forth. And we just need to check basically C, which is the stretching factor for the input with respect to the output, and then just try to find the smallest C, which captures all these response vectors. The smallest one gives us this stretching vector as an upper bound. Okay, applying this to a structural model, let's look at this plate with 100 shell elements and 110 nodes. And then we say, we look at the failure criterion that the displacement of a corner point here is more than 15 centimeters. Then we put a load according to, let's say, a load field, which is stochastic, with 4 parameters, theta1 to theta4, which are part of this model. And then represent the whole thing by Calhoun-Löwe expansion. I think here we use the squared exponential kernel, but I just made a note here because there are also investigations about the type of this kernel where we have higher efficiency and higher match with the physical background if we use a modified exponential kernel. So, but here we use the squared one, so we can also use the better one, which is a modified one, to have even higher numerical efficiency. So that just as a side note. So coming back to this load model, we see the 4 interval parameters here, and we note that theta2 is in the denominator in the sine function. So which means that the dependency between theta2 and the force is actually nonlinear and also non-monotonic, which then plays a role when we look at the solution. So then, in addition, we use 2 parameters for the Young's modulus and 1 for the plate thickness, so that we have, let's say, 6 parameters as intervals. So we need to solve an optimization problem in 6 dimensions. So then we say, okay, we apply the operator norm theory to this red box in the Calhoun-Löwe expansion 2 slides back. And then we make now slices. So we have a 6-dimensional space, 6 interval parameters, and we keep 5 of them in the midpoint and play with number 6. So just once at a time. And that shows these 6 slices here, these pictures of the 6 slices through this 6-dimensional space. So here we see we play only with the thickness of the plate. Here we play with parameter theta1 and so on. And we see, for example, when we make the plate very thick, then the failure probability, which is the blue line, becomes very small. When we make the plate very thin, the failure probability will be larger. So what we see here is the blue line representing the failure probability in dependence on the parameters. And we see the orange line, which is the associated value of the operator norm, depending on the parameter. If we now want to find the blue line, which we are actually looking for directly, we need to repeat the reliability analysis multiple times, which is very demanding. So what we want to do is we want to find the extreme points for the failure probability. So basically the largest value. So we are looking for this point here. In order to find this, we can say instead of evaluating the failure probability, we evaluate the operator norm, which is much faster, without reliability analysis, just looking at the physical problem. And we find the theta, which is the smallest value of the thickness of the plate, leads to the largest value of the operator norm. And then we pick this thickness, and then we do one shot for the reliability analysis and calculate the associated failure probability. So you may now say, okay, that's easy because in 5 of the pictures, it's a non-monotonic problem. We just use an endpoint. So why not use just vertex method or something like that? That kind of method would not find points in the middle of the interval, inside the interval, leading to largest failure probability, which we see for theta2. That is the non-monotonic dependency. And here we see a parameter somewhere out of the interval will lead to the largest value of the failure probability. But the deal is to evaluate only the operator norm to identify this theta, which maximizes the operator norm, and that is the same theta which maximizes the failure probability. So we use the operator norm to identify this maximizing theta, and then do one shot for the reliability analysis, which is very fast. So that is what we can now see in the linear and in the numerical comparison between what we do with operator norm, with brute force double loop solution, and compared to vertex method. So operator norm shows us the correct values for the operator norm and also for the failure probability when we compare this with the double loop solution. So operator norm theory gives us the correct results, But looking at the numerical effort in the last row here, we see that the numerical effort is much lower by an order of magnitude compared to double loop solution. Here, the effort is even lower compared to vertex method, while vertex method has a problem to find the upper bound of the failure probability, because that point for θ2 is inside the interval. So we can have a numerical effort which is significantly reduced by at least an order of magnitude and correctly identify even internal optimal points. So, okay, that was now a kind of example for demonstration, but that can also be used for large-scale problems. So we applied this to a 6-story building under some earthquake excitation. So that's a real size structure, and that excited by an earthquake excitation. So modulated Clough-Penton spectrum. We have 7 parameters for the load model, Young's modulus of concrete for each stories. So 13 intervals involved in this problem. And we look at the failure probability for a limit of the exceedance of the interstory drift, which is a kind of standard pathway to do reliability analysis in earthquake engineering. So here we see the result, which is comparing what operator norm theory does with 3,500 finite element calls, model calls for the whole optimization with respect to 4 or 5 million calls if we do vertex method or more brute force methods like quasi-Monte Carlo. So and still we find the endpoints, which are maximum and minimum of the failure probability, in a very efficient way. So the numerical effort is reduced significantly for these, and it's applicable even for large-scale problems. So it's not just for toy problems, can work with larger problems. Okay, but then we said, okay, we may also look at some other approaches if we want to, let's say, try to find a solution which gives us an access to also develop a bit more understanding about the problem. And that is something we developed with Marcos Valdebenito, also during his Humboldt Fellowship when he was here in Hanover. And that is using intervening variables, which is a concept which comes from optimization. So let's start with how we calculate the failure probability based on sampling. So that is, we estimate PF based on this integral, which is integral over the failure region based on the joint PDF, and using an indicator function instead of integrating just along some limit state function. So we use the indicator function to identify what is failure, what not. At the same time, we can calculate the first derivatives of PF, of the failure probability, with respect to individual parameters in the distribution models, so that we can then say this is the, let's say, first order sensitivity of the failure probability with respect to the interval parameters. And that can be estimated based on samples, let's say a brute force Monte Carlo, not only estimating the failure probability as kind of average of failure, it can also estimate the first order derivatives with the same shot, basically based on the same sample. So now when we say, okay, we have an estimate of the failure probability based on some interval parameter, parameter vector theta, and we have the first derivatives, so the slopes, we can do a linear approximation, basically first order Taylor series. So, but what is the problem? So here we see that on the horizontal axis, we have the parameter of the distribution model. The vertical axis, we have the failure probability. So this dependency is usually a nonlinear dependency, like the green line. If we do a one-shot sampling, so let's say theta naught, we get 1 point, 1 result for the failure probability. If we then also estimate the first order derivatives, we can put a tangent to this actual curve in this point. So that is okay, as long as the nonlinearity is not very strong. But if we have a stronger nonlinearity and the intervals for theta become larger, then we might be very far away from the realistic result if we do an approximation based on this linear approach. So the idea is then to introduce variables which are functions of theta, nonlinear functions of theta, in such a way that we can represent this picture not PF versus theta, but PF versus our intervening variable Q of theta. So if Q of theta removes the nonlinearity from the problem, that would mean PF of Q is a linear function. Of course, if we don't know the exact nonlinearity which is involved, we can only remove the nonlinearity approximately. So we end up with a function which is slightly nonlinear. But the strong nonlinearity will be gone because this is captured in Q of theta. And then we represent the problem in terms of PF depending on Q, so that we can estimate PF depending on the Q, depending on the theta, and at the same time, estimating the first derivatives of PF with respect to Q, and do the linear approximation in dependence on Q. And that will lead to a much better approximation. So the question is how to choose these functions Q, which are the intervening variables. So we followed an approach from optimization and say we use power type representations of these values. So what we do here is that's a parametric surrogate based on the intervening variables. And in the end, that will be a two-level approximation. So the first level of this approximation is based on the limit state surface. So we represent the original limit state surface, which was the nonlinear function in the last slide, the green curve, g of x, by a linear approximation in terms of g of eta. And eta are the nonlinear functions, the intervening variables based on power type of the physical parameters x. So we have a linear function here, a linear approximation. So now we need to find the parameters for this linear approximation. So that means the exponents m for all the physical parameters and the coefficients g for this linear approximation. So we need 2n plus 1 coefficients. So we need 2n plus 1 conditions. So the first condition is that in some specific selected point x naught, the approximation and the true functional value of the limit state surface of the performance function should be the same. Then the first derivatives should be the same and the second derivatives should be the same, which can be estimated easily based on the physical model. We don't consider the mixed terms. So just based on this information, which is relatively easy to extract, we can basically remove the nonlinearity from the problem so that we end up with this linear approximation in the right-hand side of the slide, which is the linear green function. And if we represent this linear green function in terms of the original physical parameters, it is a nonlinear function, a nonlinear approximation with respect to the original nonlinear performance function. And then this approximation, nonlinear against nonlinear, looks very good. And we can solve the whole problem in this linear setup on the right-hand side. So, but then if we solve the problem, the reliability problem, thinking, for example, about first-order reliability method, we can translate the whole problem just in mind into standard normal space. And we will find that, okay, the shape of the limit state surface will be influenced by the type of the distribution functions that are involved when we transform them into standard normal random variables. So that transformation includes another nonlinearity based on the type of distribution. So in that nonlinearity is removed with a second level of intervening variables in this way that we put another surrogate here in the argument of the standard normal distribution function, which is basically minus beta, which is the negative reliability index relating then the parameters of the distributions to PF. So there's a second level of nonlinearity removed in this way. And these components that you see here is basically minus beta, and these xi values you see here is basically the sensitivities of the reliability index with respect to the parameters theta of the distribution models. So the h can be estimated based on our sampling result. That can be done to estimate these h values, and the xi values are what you know from first order reliability method. That is basically the alpha values, which is the sensitivities, which can be estimated also depending on the parameters in just one shot, also based on the sampling result. So we have a second level of removing nonlinearities. In the first level, we remove the nonlinearity from the limit state surface or in the physical space. In the second level, we remove the nonlinearity from the transformation into standard normal space based on the non-Gaussianity of the distribution functions. So that can be made easier when we just look at normal distributions. So what is the effect here? So the effect here is that we actually have now parameters theta in our distribution models and we want to do a reliability analysis. So we put one alpha level in our, let's say, fuzzy set. So we end up with an interval. So we have an interval for a parameter of a distribution function. So then when we play with this parameter, we end up with different distribution functions for x. Then we would need, usually, if we do brute force, repeat a reliability analysis, repeat multiple times the deterministic model to end up with different distribution functions and different failure probabilities based on playing with this parameter of the distribution. We will end up with the lower and upper bound of the failure probability and put this back as one result, which is then making up the fuzzy set of the result of the failure probability. So that is very demanding. So what we actually do is just one shot. We pick the midpoint of this interval for the parameter, just one vector for the theta's, and then based on this point, we do one shot for a stochastic sampling to calculate one value for a failure probability. And then we use the information that we get from this one shot, from this sample, in order to estimate in the first place the parameters for our first level of the intervening variables. So here we need only one support point to calculate all these parameters that we need. And then we calculate also for the second level, intervening variables approximation. We can calculate the x's and the h also from the same sample. So we need only one sample to calculate all these parameters that we need in order to put up this equation, which is a nonlinear surrogate relating the imprecise parameters, the interval parameters, to the failure probability, so that we end up with a function failure probability independence on all these parameters. And now we just need to, let's say, play with the parameters in order to find the result, which is the endpoints of these intervals, and then sample the result of the fuzzy failure probability with just one shot of the sampling. So we did this for a very simple example of a displacement of let's say, a kind of foundation. And we use the structural model, finite element model, and the random parameters as the load and the Young's modulus of sand and gravel. So we have two different levels here. And then we use actually fuzzy parameters, which are relatively wide, because in geotechnical engineering, you have very, very large epistemic uncertainties. So we used very wide intervals for these parameters, which is typically a very big problem if we go just for, let's say, a linearized solution, as linearized as a surrogate based on first order Taylor. So now, using these intervening variables, we pick the midpoints from all these 6 parameters here and do a reliability analysis with a sample size of 300 and important sampling. And then, based on this one-shot result, we calculate all the parameters that we need for the intervening variables to have this surrogate, this nonlinear surrogate, PF independence on theta. And once we have the surrogate, it's very fast to calculate the result of the failure probability depending on all these thetas. And the nice result and the interesting result is that we come very, very close to the true solution. So the true solution is the purple one. So the proposed solution based on intervening variables is the yellow one. You see that the quality is actually pretty good, although the range of failure probabilities goes over 15 magnitudes here. So that is a big surprise that it really works that well, and that it can really represent and deal with even these very, very large epistemic uncertainties. So that can be done for large structures, avoiding very, very often repeated demanding analysis. It can work with moderate nonlinearities. Of course, it cannot work with very strong nonlinearities, and moderate dimensionality, and only for a single failure mode. So we need to look at failure mode by failure mode, just because of the, let's say, intervening variables used for the approximation of the limit state. But it can be used for very, very large epistemic uncertainties, even with nonlinearity. So then we said, okay, if we want to have this nonlinear surrogate, even not introducing intervening variables, because we still need to, let's say, have an idea how they might look like. Say, if we want to, let's say, do this, even without some assumption of how the nonlinearity might look like, we could try to find the surrogate as a function PF of theta based on a pure sampling-based approach. And that has been done also with our Humboldt fellow, Peng-Fei Wei, from Northwestern Polytech when he was here in Hanover during his Humboldt Fellowship. And that is a development which is called non-intrusive imprecise stochastic simulation. So the idea is here that we use extended Monte Carlo in a local way or in a global way to identify the dependency of the failure probability depending on parameter by parameter once at a time in the first place. So these equations, as you can see, look a little bit like what we do with importance sampling. So what we do in the local extended Monte Carlo is we take, for example, the midpoint of all the interval parameters, theta star, fix them in this point, and do a one-shot reliability analysis to calculate PF, independence on theta star. So then we can say we reweight the sample with this ratio of the PDF depending on theta other than theta star with respect to this value of the PDF at the point of theta star. So then we basically do a reweighting of the sample with this equation, and that way we obtain a function PF independence on theta. So theta once at a time, or you can also play 2 at a time in these things. Of course, if we just start this approximation around one point of theta star, if we go far away from theta star, the approximation might not be very good anymore. So the idea was then to sample theta as well. Sample theta from an auxiliary distribution, and then remove the influence of this auxiliary distribution by taking the expectation afterwards to average out all the results again to end up with the function PF of theta. So that way we capture a space for theta with this sampling. So both pathways are possible in order to estimate parts of this dependency PF of theta, which can then be used for so-called high-dimensional model representation, which is a series expansion for failure probability depending on distribution parameters. So here we see this is the first element in the series expansion, which is the first shot sampling result just using theta star. Then we play with the first order terms. Let's say we move only one parameter at a time here in the numerator to estimate these functions PF depending on changing only one parameter at a time. Then the second order terms is changing 2 parameters at a time. The third order terms changing 3 parameters at a time. And you can imagine that very quickly we can cut off here because the influence of that kind of very complex interaction becomes smaller and smaller very quickly. So what we do is basically we build this series expansion by estimating the terms in the series based on either the local form of the extended Monte Carlo or the global form of the extended Monte Carlo. So that's just the equations based on the estimation idea from the past slide. Nice thing with the global expanded Monte Carlo is that we can also use this for parameters that are structural parameters in form of intervals. So just sampling the parameter over some range and then taking the expectation, that can not only be done for distribution parameters, but also for structural parameters. So that is an extension which is possible on the global extended Monte Carlo. And then we can use basically just one sampling result at theta star, or even playing with theta star in the sampling-based way for the global one, and then get all the components of the series expansion from just one-shot sampling, and then even estimate the confidence bounds considering sampling uncertainty, because this is a purely statistical approach. So it gives us also the result for the quality of the result. So basically taking care of the sampling uncertainty, calculating confidence bounds, independence on the sample size that we have. So that is the basic solution, which we then also have extended together with Xingwen Zong, who was also here during the time when Peng Fei did his Humboldt Fellowship. And we expanded this also in relation to, let's say, advanced sampling methods to reduce the numerical effort even further. So one way was to develop different versions also for expansion of line sampling to have a very high efficiency, and that also with Gaussian process regression, adaptive, active sampling approaches. So for let's say kind of active learning tricking and these things for the approximation of the limit state surface. So all kinds of combinations are possible based on this general idea of the non-intrusive imprecise stochastic simulation. Then we applied this to large-scale examples in order to show that it's possible to solve large-scale problems in this way. For example, for this transmission tower with 80 bar elements, just a linear structure, 4 static loads, and in total 160 random variables. And we selected the cross-sectional area of the bars as log normal, Young's modulus as log normal, and then 40 intervals, which are the expected values of the Young's modulus and the cross-sectional area of the corner bars. So a total of 40 intervals in order to solve this problem, and then calculate the failure probability for a, let's say, limit of the displacement of some point at the top of the tower of 6 centimeters as put as threshold. So in total, the whole thing with the, let's say, expanded solution of a line sampling needed about 1,000 calls of the structural model in order to solve the whole problem. And keep in mind that was 40 interval parameters involved here. Here we have used 2 different methods, and the result tells us basically in the first place which are the most important parameters, which are intervals in this problem. So that's a very nice result, which can be used for model order reduction, because that is a sensitivity analysis, because our series expansion, high-dimensional model representation, tells us about the sensitivities of PF with respect to the interval parameters. So it's reliability sensitivity, what we do here in the first place. And then for the real actual approximation, we can limit the problem maybe to pick only 4 most important parameters in this example. So then we have a limited problem, and then we can represent the whole thing in such a way that we can say, okay, for our one-shot sampling result, our failure probability is this one, 1.6 times 10 to the minus 3. And then here we see the functions, the first order functions for these first 4 most important parameters, how PF would deviate from 0, which is basically this point, when we change the parameter. And you see that is a nonlinear surrogate of PF with respect to theta for each theta, 1, 2, 3, 4, which are the 4 most important ones here. And at the same time, the second row of the pictures here is the errors in the estimate based on sampling uncertainty. So we can have also a quality estimate of our result. So, and that kind of thing can also be used for very complex systems. So we use this for solving the older NASA challenge problem, which has 21 parameters, which come in form from distribution functions, imprecise distribution functions, intervals, whatsoever. And it's a combination of 5 different disciplines involved, 8 limit states. And that is a highly nonlinear problem with an unknown, let's say, physical model behind. It's just based on samples. And in the end, we have 8 limit states to check. And here we see the big mess. 21 parameters, can be anything, can be an interval, can be whatever kind of distribution with parameters that are intervals and these things. And the question was, what are the most important parameters and what is the reliability of the problem depending on these parameters? So with this high-dimensional model representation and NISS method, we were able to do this kind of sensitivity analysis in the first place to identify what are the most important parameters. So one is standing out in a significant way, but in total, I think we use 6 parameters here to, let's say, calculate these dependencies. And then we see these first order dependencies here in the model. So the nonlinear surrogate 1 by 1 for each of the 6 parameters, as you can see. And you see the red lines, which are the 95% confidence intervals based on the sampling uncertainty that we got. So and here we also have estimated the second order terms of the HDMR, including the 95% confidence intervals. And the nice thing is that this method does not only produce better results in terms of quality with respect to previous methods, but also with, let's say, significantly reduced numerical effort. So the numerical efficiency is significantly better than with other methods that were available at this point and even now. So to summarize, so we have now seen 4 methods specific methods to solve these problems of reliability analysis with imprecise probabilities for pathways, all under the topic of optimization approaches, some intrusive, some not intrusive. So all these methods are compatible with stochastic approaches and techniques, so we can use the complete framework of stochastic analysis. We are not limited in that case. And we can apply this to nonlinear and even high-dimensional problems. So we can go for a quantitative set theoretical consideration of epistemic uncertainties in this way, even with, let's say, a variable size of our intervals related to a variable confidence level. And we have a comprehensive reflection of imprecision in the computational results and calculate bounds on probabilities depending on the confidence of the expert in the specification and quantification of the epistemic uncertainties. We can also identify sensitivities with respect to the imprecision of the structural and stochastic models by playing with the interval size of our interval parameters. Should it be structural parameters or distribution parameters? So in that way, we can come up with realistic models, efficient numerical analysis, and we hope that this contributes to better uncertainty quantification for industry-sized structures and systems, and then later on for improved design, performance, and reliability of our structures. So with that, I would end my presentation, and thank you very much for your attention.